All right, so now we're going to talk about discrete momentum maps associated with variational integrators. And before doing that, I'm going to sort of remind you of momentum maps on the tangent bundle and cotangent bundle, just so that it's clear how they're related to the discrete momentum maps, which show up. Okay, so if we recall, it's like momentum maps are essentially, it's like these objects which are preserved by the flow of Lagrangian Hamiltonian systems if the Lagrangian or Hamiltonian has a group invariant Lagrangian or Hamiltonian. Okay, so at the continuous level, sort of. They are, of course, sort of on the Hamiltonian side, and then on the Lagrangian side, you have the following. So on the Hamiltonian side, you have a map J from the cotangent bundle to the dual de Lie algebra. Okay, and it's defined in the following way. A depends on an element of the cotangent bundle, so I denote that by alpha q. And then it gives you something which is in the dual Lie algebra, which is to say that it acts on a Lie algebra element in a linear fashion. So I define it by having it act on a Lie algebra element. Okay, and then this turns out to be given by, all right, so alpha q is a covector. You can think of it as acting on the infinitesimal generator associated with the algebra element. Okay, and so this is the definition. It's like, if you will, of the Hamiltonian version of the momentum map on the cotangent bundle. And then let's see what happens on the Lagrangian side. Okay, so let me give you a little more space. So on the Lagrangian side, right, you have something which I call J sub L, okay, which is a map now from the tangent bundle TQ to the dual of the algebra. Okay, all right, and I have JL acting on now an element of the tangent bundle VQ. All right. Sort of just let me remind you that there are all these discrete discrete fiber derivatives. It's like, and continuous fiber derivatives which relate TQ with T star Q. It's again with Q cross Q, right? So if you have something on T star Q, there is the Legendre transform of the continuous fiber derivative, which maps TQ to T star Q, and then you have the discrete Legendre transforms, which map Q cross Q to T star Q. Okay, so as you might expect, it's like the way this is defined, if you will, is by essentially pulling back the Hamiltonian momentum map. It's like to give you this Lagrangian momentum map. Okay, so what you do is that this is equal to the pullback of this. So this is J applied to FL of VQ, because C. Okay, and so this is telling you that JL is the pullback by the continuous Legendre transform of the cotangent bundle momentum map. Okay, so all right, so with that observation, then it's not so surprising that the discrete momentum maps are defined in a similar way to this. Okay, so on the discrete Lagrangian side, right, you have what I call JLD, for lack of a better term, or maybe let's just call it JD. Right, J discrete. Okay, and it's a map from Q cross Q to the dual to the algebra. Okay, so so what you expect is that JD, say Q0, Q1, right, paired with the algebra element. Sorry, this is paired with the infinitesimal generator, right? All right. Okay. So that thing. No, I'm sorry. That's not what I meant to say. Right. All right. So let me just write it this way. So going from here to here, it's like I'm doing a pullback. This is still the Lie algebra element, but this is equal to the fiber derivative of the vector applied to the infinitesimal generator. Okay. All right, so that's right. And again, that means that JL is the pullback by the continuous Legendre transform of J. Okay, so I want to define, it's like JD, which is the sort of momentum map associated with the discrete momentum, the discrete Lagrangian. So the discrete momentum map here. Okay, so that, as you might expect, is also defined with respect to pullback. Okay, so you get, well, you get J applied to FLD plus minus Q0, Q1 paired with the algebra element. Okay, and that's going to be equal to, for example, minus D1 LD Q0 Q1 paired with the infinitesimal generator evaluated at Q0. Okay, and that's because, of course, this momentum has an interpretation of being a covector at the point Q0, so it has to be paired with a vector at the point Q0. Right. Or you could equivalently write this in terms of D1LD, right, depending on which of the discrete fiber derivatives you've chosen. Okay, so so that's this idea of a discrete momentum map, and again, it's sort of related in the obvious way to the cotangent bundle momentum map, the same way that the continuous sort of Lagrangian momentum map is related to the continuous Hamiltonian momentum map via the continuous fiber derivative or Legendre transform. Right, the discrete momentum map is related to the momentum map on the cotangent bundle via the discrete Legendre transforms. Okay, so now let's try to prove that this thing is preserved, at least if you have a discrete Lagrangian which is group invariant in some way. Okay, so this is basically the content, if you will. It's like of a discrete Noether theorem. Okay, so let me just write that JD Q0 Q1, right, because C is minus D1 LD Q0 Q1 paired with CQ Q0. Okay. All right. So now let me state a discrete Noether theorem. All right. So if you recall the continuous Noether theorem, it says that if the Lagrangian is invariant under the tangent lifted action of the group, it's like on the configuration manifold, then the Lagrangian momentum map is preserved by the flow of the old Lagrange equations, or on the Hamiltonian side, if the Hamiltonian is invariant under the cotangent lifted action of the group on the configuration manifold, then the cotangent bundle momentum map is preserved by the flow of Hamilton's equations. So, so in the statement of the discrete Noether theorem, you might expect that what you need to be able to talk about is what the notion of invariant under the lifted action should be. Okay, and in that setting, the appropriate notion of group invariance or discrete Lagrangian is that it's invariant under the diagonal action of the group on both copies of Q. Okay, so a discrete Lagrangian let's see, LD, which is a map from Q cross Q to the rails, right, is sort of G invariant under the diagonal action of G on Q cross Q, right, if LD of G acting on Q0, G acting on Q1, right, it's diagonal because it individually acts on each copy of Q separately, is equal to LD Q0, Q1. This is true for all G group elements in the group. Okay, so we say that the discrete Lagrangian is G invariant under the diagonal action if this condition holds, right? And if so, then the discrete momentum map JD, which is a map from Q cross Q to the dual of the Lie algebra, right, is preserved, right, by the flow of the discrete Lagrange equations. Okay, so this is the discrete version of Noether's theorem is that if there is a discrete Lagrangian and it is invariant under some appropriately lifted action of the group on the configuration manifold, and in this case that appropriately sort of lifted notion is this idea of the diagonal action on the two copies of Q. If that is the case, then there's a discrete momentum map, right, defined in this way by pullback, if you will, of the cotangent bundle momentum map. Then that discrete momentum map is preserved by the flow of the discrete Lagrange equations. So let's try to prove that. Okay. Okay. So we're going to use the fact that the discrete Lagrangian is G invariant under the diagonal action, and we're going to do this in the following way. So let's consider an element of the dual of the an element of the Lie algebra, because C is an element of the Lie algebra, right? If you're an element of the Lie algebra, you can exponentiate it to give you an element of the group. All right. So if you have this, then the exponential of h times cos C is an element of the group. Okay. So we can use this element of the group and act on the two copies of Q diagonally. So this implies, right, so G invariance of LD implies that LD exponential of h times cos C acting on Q0, exponential of h cos C acting on Q1, right, is equal to LD of Q0, Q1. Okay, so this is again just coming from the definition of G invariance, which needs to hold for all group elements. Okay, right. Then you can differentiate this. Well, I'm not call. Okay, maybe I shouldn't call it H and call it S. Okay, so let's say S. Okay, and then I want to differentiate this condition. It's like with respect to s, and then evaluate it s equals to 0. So I differentiate with respect to s and evaluate at s equals to 0. Okay, and when you do that, of course, s shows up in both slots, so you have to have the derivatives with respect to the first and second slot. And then you evaluate it at s equals to 0, so that's q0, q1. And then you have to multiply it by the, the derivative of this thing. And of course, by definition, if you will, this is really just the infinitesimal generator of Cauchy evaluated at q0. Okay, so this is Cauchy q0, right? So this is really this pairing plus d1 or d2 LD q0 q1 paired with Cauchy q at q1. And this thing is equal to 0 because this right-hand side is constant with respect to s. But we're on a solution of the Euler-Lagrange equation. So we restrict ourselves to a solution of the Euler-Lagrange equation. And on a solution of the Euler-Lagrange equation, we have the property that d2 LD q0 q1 plus d1 LD q0, sorry, d2 LD q0 q1 plus plus d1 LD q1 q2, right, is equal to 0. And in particular, I can pair this with an element of, it's like of the tangent vectors, right? So this is essentially a one form. Okay, I can pair it with a tangent vector. So let's pair it with, Cauchy q1. All right, so you pair this. So I have d2 LD q0 q1, right, paired with Cauchy q1 plus d1 LD q1 q2 paired with Cauchy q1. That whole thing is equal to 0. Okay, so I have this equation, and then I can take the difference of the two. Okay, so let me just erase this. Okay, so let me subtract this from this. Okay, so these terms cancel. And then, well, it doesn't really matter which I subtract from. Okay, let's take this and I subtract this, right? So these two terms cancel. I'm left with d1 LD q1 q2 Cauchy q1, right, minus d1 LD q0 q1 paired with Cauchy q0, right, is equal to 0, or, right, minus d1 LD q0 q1 paired with Cauchy q0, right, is equal to minus d1 LD q1 q2 Cauchy q1. All right, and of course, if you can see that that's the momentum maps, right? So this is telling you that JD at q0 q1, right, is equal to JD at the discrete Lagrangian map applied to q0 q1. Okay, or if I prefer, I can write this as the discrete Lagrangian map pullback of JD q0 q1. So this is telling me that JD is equal to the pullback by the discrete Lagrangian map, which is of course the flow of the discrete Euler-Lagrange equations of the discrete momentum map. So discrete momentum pulled back by the flow of the discrete Lagrange equations is the discrete momentum map itself, which basically means then that the discrete momentum map is preserved by the flow of the discrete Lagrange equations, which is what we wanted to prove. Okay.